so this is the third lecture on holomorphic Poisson structures. In the previous lectures, we were speaking mostly about the local structure of holomorphic Poisson manifolds. And particularly in the last lecture, we saw that any holomorphic Poisson manifold carries a natural foliation, the so-called symplectic foliation. This is the foliation which is generated by the Hamiltonian vector fields. So it gives a subsheaf in the tangent sheaf, which is spanned by the Hamiltonian vector fields. And a key feature of this foliation is that all of its leaves carried a holomorphic symplectic form. And at the end of the previous lecture, I also mentioned that there was an additional foliation present, which you get by taking the symplectic foliation and adding one more vector field as a generator. This is the so-called modular vector field, which acts like a kind of divergence of the Posson tensor in local coordinates. So I should emphasize that really the symplectic foliation is the most studied and it's the most central feature of the geometry, but in various circumstances it's also useful to look at this additional modular foliation. And we'll see that more next time. Today, what I want to talk about is a case where these are actually the same. And that's the case of a regular Poisson manifold. So a Poisson manifold is called regular if the rank of this bivector field pi is constant. It doesn't change anywhere in the manifold. So remember that we have a local picture for Poisson manifolds given by the Darboux-Weinstein coordinates. So in particular, in the case of a regular Poisson manifold, this tells us that we can find coordinates which come in groups p, q, and z, such that the Poisson structure looks locally like the sum del qi wedge del pi. And then if you calculate this modular vector field, which recall is the divergence of the Posson tensor, well, it's the divergence of something constant, so it's 0. So the upshot is that the symplectic leaves and the modular leaves are the same. This zeta doesn't add anything new to the symplectic leaves. And the picture, remember, is that the symplectic leaves are moving in the q and p directions, keeping z constant. So here's a rough picture of what that looks like. Okay, so the local picture of a regular Poisson manifold is very simple. They all look the same locally. The only invariant is the rank of the Posson tensor, which tells you how many p's and q's there are. So today I want to focus more on the global aspects. So by that I mean, let's consider the case where this manifold X is actually compact. And then there are various questions one could ask. For instance, we could ask whether the leaves of this foliation are also compact. Maybe they are, maybe they aren't. We always know that they're immersed submanifolds, but an immersed submanifold doesn't need to be closed. And then we could also ask about the classification of these kinds of Poisson manifolds. So we have a compact Poisson manifold with a regular Poisson structure. We may ask what it looks like globally, and can we list them all, for instance? So let me begin just by giving a few fairly simple-minded constructions of regular Poisson manifolds. So the most silly example is that we can take X to be any complex manifold, and then we can just give it the bivector, which is equal to 0. Well, that clearly has rank 0 everywhere, so it's regular by definition, and the symplectic leaves are just the individual points of X. The foliation is not very interesting. At the opposite extreme, we could consider the case where the Poisson structure is non-degenerate everywhere. Remember, that means that we can invert it to get a holomorphic symplectic form. And then the leaves are simply the connected components of X. So that's, again, a regular Poisson manifold. Somehow, in between these two, we could take a pair of regular Poisson manifolds, X and Y, and then we can form their product. Well, the rank of the product will just be the sum of the ranks of X and Y, so that will be a regular Poisson manifold. On the other hand, if we're given a regular Poisson manifold, then we could take a covering space of X, say X tilde. A covering space is locally diffeomorphic to X, and so we can take the Posson tensor on X and we can pull it back to get a Posson tensor on X tilde, and locally those will be isomorphic, so the Poisson structure which you get on the covering will also be a regular Poisson structure. And somewhat going in the opposite direction of the previous example, we could take a discrete group G, which acts on a regular Poisson manifold freely by Poisson isomorphisms. And let's assume that we're in a nice situation so that the quotient is actually a manifold. Well, as we saw, you can always take a quotient. The quotient will always carry a Poisson structure. And in this case, again, the quotient map from X to its quotient is a covering space. So going in the reverse direction of the previous example, what we get is a Poisson structure on X mod G, which is regular. So as an example of this previous construction, we could look at Abelian varieties. So let's start with vector space V, which is isomorphic to Cn, so an n-dimensional complex vector space. And let's consider a constant bivector. So it's an element in wedge 2 of this vector space, which remember we can think of as being a constant bivector field on V using the standard trivialization of the tangent bundle. And let's look at the image of the anchor map of this Poisson structure, which is a subspace in V. It indicates the tangent space of the symplectic leaves. So the symplectic leaves then are just given by affine linear subspaces in this vector space V, which are given by taking a vector in V and considering a translation by any element in this subspace W. Yeah, so again, it's a picture like we had on an earlier slide. If I were to choose a nice basis for V, I would have my coordinates P and Q, and this subspace W would be the one spanned by the P's and Q's, and then to get the other symplectic leaves, I just translate that subspace by some vector in V. Okay, so now let's consider also a lattice inside V. So that's a free Abelian group of rank 2n, which sits inside V and spans it as a real vector space. And then the quotient, X, which is V mod lambda, provided that we have this full rank hypothesis, this will be a compact manifold, and it will be diffeomorphic to 2n torus. But it carries some complex structure which depends in general on the lattice lambda. So this is what's called the compact complex torus. And in the particular case where this compact complex manifold can be embedded into projective space, it's called an Abelian variety. And notice that it's always a group because it's the quotient of the additive group V by an additive subgroup lambda. So now we can consider what is the leaf through some point in this quotient V mod lambda. Well, that corresponds to the equivalence class of some element in the vector space. And so all we have to do is take the symplectic leaves up in our vector space and project them down to the quotient. And when we do that, what we'll get is, well, simply given by taking this point in X and translating it by the image of W using the group law on this Abelian variety. So when you use the isomorphism theorem, you see that this image is exactly isomorphic to the quotient of W by the intersection of W with the lattice. So in particular, the leaves here, which are given by this quotient of W, they will be compact if and only if this intersection lambda and W is a full rank lattice inside of W, so that the quotient is again a torus of dimension equal to the dimension of W. But observe that this is very much not the generic situation. So in particular, if W is a proper subspace of V, then generically, the intersection of this lattice with the subspace will be 0. So actually, the leaves are isomorphic to W. You see this, just notice that if you have a subspace sitting inside a vector space, and now you want to specify also a lattice, you're free to choose the basis of that lattice lying off the vector space. It's easy to do that. That's a generic situation. So for these complex tori, what's happening is that the leaves are almost never compact submanifolds. The typical case is that they're actually isomorphic to some vector space, which has been immersed in a dense way inside this torus. That's about all I'm going to say about this issue of compactness of the leaves. I want to focus mostly today on the global structure and classification of these constant rank Poisson structures. So to conceptualize it, it's helpful to draw a picture of the relation between the rank of a Poisson manifold and its dimension. So here's a plot. The black dots correspond to allowable pairs of rank and dimension. Now, this red line is the diagonal. That's where the rank is equal to the dimension. And there's nothing above that because the rank can never be bigger than the dimension of x. On the other hand, we also know that pi is skew symmetric, so the rank is always even, so you'll never see anything along the horizontal lines corresponding to odd values of the rank. So that explains the rough structure of this picture. So it's useful to organize the classification very roughly by, first of all, the dimension of x. Of course, as the dimension increases, the complexity of the space typically increases. On the other hand, the complexity tends also to increase with not the rank, but rather the co-rank. So the difference between the dimension and the rank. So here, these red lines, those correspond to pairs which have the same co-rank. Okay. So somehow the simplest case is when the co-rank is equal to 0, so the rank is equal to the dimension of x, and that's this blue line, which is the boundary of our region. So if the co-rank is equal to 0, that means that the Poisson structure is non-degenerate. So that's the case of holomorphic symplectic manifolds. Let's start there. So let's start even with the simplest case of a holomorphic symplectic manifold, which is bigger than a point. That would be the case of a surface. So now we have X being a compact symplectic surface, and let me furthermore assume it's connected. What can these things look like? Well, the Posson structure is non-vanishing. It's a section of wedge 2 of the tangent bundle, which is the determinant of the tangent bundle. It's an anti-canonical section, as we saw previously. So what this tells us is we have a non-vanishing section of the anti-canonical bundle, so the canonical bundle, or equivalently the anti-canonical bundle, must be trivial. And then notice that this Poisson structure must be unique up to rescaling, because on any compact complex manifold, the only global holomorphic functions are the constants. So once we specify this, this manifold X with its complex structure, there will be a unique Poisson structure up to rescaling. Now, there's a classification of the minimal complex surface. This is one of the great results in algebraic geometry due to Enriquez and Kodaira. And part of their classification explains what all the possible compact connected symplectic surfaces can be. So there's a very short list. It's one of the following. It could be a complex torus, C2 mod lattice, like we saw in the earlier example. It could be a somewhat twisted version of this called a primary Kodaira surface. So this is a bundle of tori over tori. So here we have a base, which is a curve. It's an elliptic curve, so it's a torus C mod lattice. And the space X is a bundle whose fiber is also an elliptic curve. So it's some kind of twisted version of this torus construction, and you can imagine building a Poisson structure on there by a similar quotient procedure to what we did for the case of complex tori. And finally, perhaps the most interesting examples are the so-called K3 surfaces. So these are the only ones which are simply connected. They're all diffeomorphic to the surface in P3 cut out by a quartic equation, so an equation of degree 4. So the quartic surfaces in P3, they give a collection of K3 surfaces. Not all K3s arise in that way, but they're all diffeomorphic as a C infinity manifold to such a thing. The complex structure and the symplectic form may be different. So that's it for compact symplectic surfaces. The study of all these different examples is a very rich subject, but I'm just going to skip right over it and continue on to the higher dimensional situation. So how can we construct holomorphic symplectic manifolds in higher dimension, which are still compact? Well, the most obvious thing we could do would be to take a bunch of compact symplectic surfaces, like on the previous slide, And then we could take their product. So I can put a symplectic form on this product space simply by pulling back the symplectic form on each factor and adding them up. This will be closed because the forms omega I are closed, and it'll be non-degenerate because we've somehow taken care of the entire candidate space by pulling back these non-degenerate forms on each factor. And I can do something slightly more general. I could take these different forms and I could weight them by some constants, lambda. Clearly, that won't change the fact that the form is closed, and as long as the constants are all non-zero, then this thing will also be non-degenerate. So in that way, we get a symplectic manifold of dimension 2n. And this symplectic form depends non-trivially on these n parameters. So in particular, the cohomology class of this symplectic form will change if you change these parameters, lambda I. But this is a kind of silly construction. Of course, we can just take products to get more and more examples. And so you may ask, what about examples that cannot be written as a product of two other symplectic manifolds? So for this one introduces the notion of an irreducible symplectic manifold. So an irreducible holomorphic symplectic manifold, abbreviated IHSM. This is a compact Kähler manifold X. This Kähler hypothesis is stronger than just saying that's a compact complex manifold, but it's important in the theory. So this is a compact Kähler manifold which carries a holomorphic symplectic structure, omega. And the part that makes it irreducible is the fact that this symplectic structure is unique up to rescaling. So the space of holomorphic 2 forms is spanned by omega. It's a one-dimensional vector space. So of course, any symplectic surface had this property. Those are all irreducible holomorphic symplectic manifolds, at least the Kähler ones. And there's a deep theorem, which is called the Bovil-Bogomolov decomposition theorem, which explains the structure of varieties with trivial canonical class. And this is a particular case of this theorem. It says that every compact Kähler manifold, which carries a holomorphic symplectic structure, has finite a tau cover, which is a product of these irreducible holomorphic symplectic manifolds and some symplectic tori. So from that point of view, the classification really boils down to understanding these irreducible ones. Up to passing to covering spaces and taking products, they kind of tell you everything. So this result, this Bovil-Bogomolov decomposition, is a very deep theorem, has an interesting history, and as part of the thematic program that this virtual event is part of, Bovil gave a very nice lecture on the history of this decomposition theorem, so I'd encourage you to have a watch of that video. Okay, so how can we construct irreducible holomorphic symplectic manifolds? Well, here's one way. Again, we start with a surface, a symplectic surface. Let's take one of these K3 surfaces. And instead of considering the product of y, we could consider what's called the symmetric product. So I take y to the n, the ordinary product, but then I mod out the action of the symmetric group, which permutes the factors. Now, provided I use the same symplectic form on each factor of y, that symplectic form will be invariant under the action of the symmetric group, and so it will induce a Poisson structure on this quotient, which is called the symmetric power of y. Now, it turns out this quotient is a singular Poisson variety. It's not a manifold. But the smooth locus is, of course, a manifold, and there the Poisson structure is symplectic. So this thing is very close to being a symplectic manifold, except it has some singular locus. And it has a very famous resolution of singularities, which is called the Hilbert scheme. You think of the symmetric power as corresponding to collections of points in Y counted with multiplicity, then the Hilbert scheme corresponds to subschemes in Y of total multiplicity n. So this resolution of singularities corresponds to blowing up some pieces of the symmetric power, which are singular, to get a smooth space. And the key feature of this Hilbert scheme from the point of view of symplectic geometry is not only that it's smooth, but also that the Poisson structure on the symmetric power lifts to a unique Poisson structure on the Hilbert scheme, which is symplectic, and is indeed giving us an irreducible holomorphic symplectic manifold. Another example along similar lines, we could try to do the same construction using an Abelian surface, so C2 mod lattice, rather than a K3 surface. Then we would get a Hilbert scheme, which was again a holomorphic symplectic manifold, but it would not be irreducible. The cohomology would be a bit too big. But there's a way to cut it down, and that's to observe that because Y is a group, there's a map which adds endpoints together to give me another point in Y, and this lifts to a map from the Hilbert scheme of Y to Y itself. And now if we take a fiber of this map, then that fiber will be an irreducible holomorphic symplectic manifold. These are the so-called generalized Kummer varieties. And then along similar lines, there's another way to cook up irreducible holomorphic symplectic manifolds starting with a symplectic surface. So rather than considering these Hilbert schemes, you consider more general moduli spaces of sheaves on these surfaces. And those are typically singular, but Mukai observed that there's always a symplectic form on the smooth locus. And so you can try to resolve the singularities of these spaces to get new symplectic manifolds. Often this doesn't give you anything new, but O'Grady realized that by making certain choices of the parameter for these sheaves, you could get a couple of new moduli spaces, new spaces which were not isomorphic to either of the ones above, not even diffeomorphic as C-infinity manifolds. And this way he produced two new families of IHSMs, one family corresponding to dimension 6 irreducible holomorphic symplectic manifolds, and another family of dimension 10 examples. So here we have two series, the Hilbert schemes of K3s. Those come in infinite series of families parameterized by this integer n. Similarly, these generalized Kummer varieties, there's an infinite series of those. And then we have these two sporadic examples in dimension 6 and 10 called the O'Grady manifolds. It's possible to construct other examples of irreducible holomorphic symplectic manifolds. But the last I heard, all of the known examples were essentially just deformations of these previous examples. So in particular, they have the same underlying C-infinity manifold, and the only way to change the example, get something new from the previous slide, is just to take the complex structure in the symplectic form and deform them. So in terms of our picture, we could kind of say that along this blue line, corresponding to the irreducible holomorphic symplectic manifolds, or the holomorphic symplectic manifolds, the whole picture is somehow generated by surfaces. So we have these three types of surfaces, and then starting from those, I can make various constructions of moduli spaces, Hilbert schemes, and so on, and that produces new examples, which I can then deform, and those will give me all the irreducible holomorphic symplectic manifolds that we know about, and then everything else by the Boville-Bogomolov decomposition is products of those things and étale covers. So somehow the symplectic piece is just, at least the part we know about, is generated by the surfaces. And it's a major open question whether we can find new examples which somehow don't arise from surfaces in this way. It's a very interesting topic. There's been a huge amount of very beautiful work on these irreducible holomorphic symplectic manifolds. But since my job is to talk about more general Poisson manifolds, I'm going to have to skip over all of that beautiful work and move right along to the next case, which is co-rank 1. So now I consider a Poisson structure where the rank is 1 less than the dimension of x. So that means that the dimension of x now has to be odd, not even. So again, let's have some examples of co-rank 1 Poisson structures. Well, one thing I could do is to take a symplectic manifold, y comma pi, and then I could just take a curve, z, equipped with the 0 Poisson structure, and then I could take the product. And this will give me a Poisson manifold, which is regular of co-rank 1. And the symplectic leaves of this Poisson manifold, they're just copies of y indexed by the points in this curve z. Along similar lines, I could consider a product of a symplectic manifold y with a torus T, which is a co-rank 1 Poisson structure. So this torus T will be odd dimensional. And then a slightly more sophisticated example, which is still somehow in the same flavor, is a kind of twisted product where I start with a symplectic manifold again. And now, instead of considering a product of with a curve, what I consider is a fibration, which is a P1 bundle equipped with a flat connection. Remember, a flat connection means that I can lift tangent vectors on y to tangent vectors on x, and this operation is compatible with the Lie bracket. So as a consequence, I can take the Poisson structure pi y on y, and I can consider its horizontal lift, which gives me a Poisson structure on x, which maps down to the Poisson structure on y. So this is a Poisson map. And if you like, you could think that actually the second example and the third example are somehow very close to the first example. If I would allow myself to consider symplectic manifolds and curves which were not compact, then I could get these other examples by taking a product with a curve in this way and then taking a quotient by the action of a discrete group. And the amazing fact, which is due to several people, all of whom are speakers or organizers of this very nice event, it says the following. So let's suppose that we have a compact scalar manifold. And we have a Poisson structure which is regular of co-rank 1, but let's only assume that it's regular away from some subset of codimension 3. Then actually it must be regular everywhere, it turns out. And moreover, this Poisson manifold, X, it has an étale cover, which is given by one of the three examples above. So quite remarkably, the co-rank 1 case is very nearly classified by the co-rank 0 case. So these constructions, you see the most sophisticated ingredient in any of these constructions is the symplectic manifold Y. And then we apply these formal constructions of taking products or flat P1 bundles. So somehow to understand the classification of these things, it really boils down to understanding the classification of these symplectic manifolds. So what about the landscape now? So we've already seen that the co-rank 1 case is somehow, at least as far as we've seen so far, somehow generated by the symplectic surfaces. And now this previous theorem is telling us that actually the co-rank 1 case is somehow also controlled by the symplectic case. So once I generate this first blue line, I basically know what's going along on this second blue line as well. It's quite remarkable. Now, as you go up in higher co-rank, the situation becomes more complicated. There are some results, including results of the authors on the previous slide. I'm not fully up to speed on the status of this problem in higher co-rank. So in the remainder of the lecture, rather than focusing on the details of these structures, I'd like to just mention one general topological observation, which is going to be relevant for us even when we consider the case where the rank is not constant. So this applies to a regular Poisson structure of arbitrary co-rank. So this is going to be a topological constraint on the manifold. And it's going to make use of characteristic class theory. So let's consider, or let's recall that every vector bundle, every complex vector bundle on a manifold has an associated cohomology class called its Chern character. So this is a cohomology class of mixed degree. The Chern character of E is a sum of CH sub j, where CH sub j is a class of degree 2j in the rational cohomology. If you're not familiar with this, it's okay. Let me just give you some useful properties of the Chern character. So the first thing is that the Chern character of a vector bundle depends only on the isomorphism class of the vector bundle. So if you have two bundles which are isomorphic, then they have the same Chern character. The next property is that if I take the direct sum of two vector bundles, then the Chern character is additive. So the Chern character of the sum is the sum of the Chern characters. You could also imagine replacing a vector bundle with its dual, and this has the effect of flipping the sign of the odd components of the Chern character. So whenever j is odd, you get a minus sign, and whenever j is even, the sign stays the same. You could also consider what happens if you have a map between two manifolds, say F, then you could pull a vector bundle back along that map, and the Chern character of the pullback is the pullback of the cohomology class given by the Chern character. And finally, a very silly observation, which is that the Chern character has to vanish when j is bigger than the complex dimension of x, and that's simply because the whole cohomology vanishes beyond that degree. So using these properties of the Chern character, I'm going to explain some constraints on the topology of X. So I particularly want to consider the case of a holomorphic Poisson manifold, and I will want to look at the Chern character of its tangent bundle, which is typically abbreviated just by the Chern character of X. So for instance, let's consider the case of a symplectic manifold. Well, for a symplectic manifold, the Poisson structure is non-degenerate. It gives an isomorphism between the tangent bundle and the cotangent bundle. So in light of these properties above, well, first of all, first property says that it depends only on the isomorphism class of E, so the Chern character of the tangent bundle is now the same as the Chern character of its dual. But on the other hand, the Chern character of the dual has a change in sign in the odd components. So the only way this is possible is if the odd components of the Chern character are all 0. Okay, so if you have a symplectic manifold, a holomorphic symplectic manifold, then the odd components of its Chern character are 0. That's a topological constraint on this complex manifold. Easy to construct lots of examples of complex manifolds which don't have this property. Okay, so continuing in this vein, let's now consider the case of a regular Poisson manifold where the symplectic leaves of this Poisson manifold are given by the fibers of a map to some other manifold Z. So in that case, the codimension of the symplectic leaves, or in other words, the co-rank of the Poisson tensor, is exactly the dimension of this space Z. So I'll just abbreviate that number by C. So now, whenever we have a fibration, there's the standard exact sequence for the tangent bundle. So a tangent vector on X can be projected to a tangent vector on Z using the differential of F. And the kernel of that map is the tangent space to the fibers. Well, the fibers are exactly the symplectic leaves. So their tangent space is exactly this subbundle in the tangent bundle, which is given by the span of the Hamiltonian vector field. So it's the tangent bundle of the symplectic leaves. So now let's consider what this means for the Chern character. Well, remember the Chern character is additive. So that means that the Chern character of the tangent bundle must be the sum of the Chern characters of the tangent of Z and this F pi. So here I've written an exact sequence, but I can always split it as C-infinity vector bundles. So this writes Tx as the direct sum of these two other bundles so that the Chern character adds. Now, arguing as we did in the previous slide, if we have a symplectic form, that will give a pairing on F pi, which makes it isomorphic to its dual. So just as we argued for symplectic manifolds, the odd component of the Chern character is 0, so too the odd component of the Chern character for this vector bundle F pi must be 0. And meanwhile, we had this other observation that the cohomology ring of Z vanishes beyond twice the dimension of Z. But you see this other bundle here is the pullback of a bundle on Z. And so its churn character is the pullback of a class on Z. And therefore, this thing must vanish as soon as J is bigger than the dimension of Z, which is exactly the co-rank of the Poisson tensor. So in this particular situation of a regular Poisson manifold, which is a fibration over some base Z, we get some vanishing of some components of the churn character. It's not true that they all vanish, but the odd components beyond the co-rank have to vanish. Now, actually, we can take this example and we can generalize it into a theorem. The generalization is in two ways. So first of all, I can drop the hypothesis that this manifold is a fibration over Z and just have a regular Poisson manifold. Morally speaking, any regular Poisson manifold is not very far from this example. You could consider the space of all of its leaves. In good situations, that will be a manifold, and it will be a fibration in this way. But in general, the leaf space may not be a manifold. But there's a way of still pretending that it's a manifold and getting some vanishing of characteristic classes, which is called Bott's vanishing theorem. So if you combine Bott's vanishing theorem with this simple-minded calculation about the churn character, what you see is that if you have a regular Poisson manifold with co-rank C, then you can take any polynomial in the odd components of the churn character, and as soon as that polynomial has total degree at least k, bigger than the co-rank C, it will have to vanish. So this gives a pretty strong constraint on the topology of a regular Poisson manifold. Any polynomial in the odd components of the churn characters of sufficiently high degree has to vanish. There's a very special case of that. Here's a very simple polynomial in churn characters. You take the degree 1 part, that's odd, and now you raise it to the power C plus 1. Let's suppose that that class is non-zero. Then we conclude that there can't possibly be a regular Poisson structure which has co-rank C on X. So this rules out the existence of regular Poisson structures on a very, very large class of complex manifolds. So in the next lecture, we're going to make use of this and study the case where this class is non-zero and we have Poisson structures which are not regular anymore.